Okay, so today we're moving on to chapter 1, section 2. We're going to talk about parametric curves. So we already talked about like parametric equations. Okay, let's make a little space here just to remind ourselves. Okay, this insert spaces. There we go. Okay, so we've already learned about parametric curves, like, oops. My view is off. I want 300%. Come on, zoom in. Ah, there we go. I want like x of t equals something. I don't know, let's just make it up. 3t plus 1. We want y of t equal to something. Let's just say t minus 1. And then we define the domain of the parameter. Let's say it goes from -3 to 2. Okay, that's going to give you some curve. Actually, let's make this a 3t squared plus 1. So this thing is going to be some sort of parabola that opens up and down. Might look, I don't know, I'm just making this up. Let's just say it looks something like this. Let's say it starts like right here and moves along the parametric equation like so. Okay. So this is part of a parabola. In Calculus 1, what did we learn to do with these sorts of graphs? So like what was Calc 1 all about? What was it about? Tells me. What did we learn about in Calc 1? Okay, people are typing in the chat. Let's see what they say. Yeah, finding the slope and limits. Yeah, you use... Okay, I'm going to mute you. Okay, thank you. You did it yourself. Okay, so let's zoom in a little. You could basically specify a point. You could say like, hey, right here at this point, what's the slope of the tangent line? Okay, now if you had the equation, like let's just say the rectangular equation, let's say it was y equals x squared plus 1, it'd be pretty straightforward to find the slope of the tangent line. What exactly would you calculate to find the slope of the tangent line? Like what is the thing that you're going to need? Right, but of what? That's what I'm asking you. You need a derivative. The derivative of what? Yes, thank you. So you need dy dx. It will be equal to the slope of the tangent line at that point. That's what I'm talking about. Cool. Yeah. So we're still interested in doing those sorts of things. That's why I'm bringing this up. We want to do exactly that, but we want to do it for our parametric curves. So how do we do that? That's what we're going to talk about today. So we're going to talk about derivatives. So we're wondering, how do we calculate the slope of the tangent line for a parametric curve? And there's actually a couple different ways that you could go about this. You could transform the parametric equation into a rectangular equation and then take the derivative. Because we learned how to do that last time. What is it called when you transform the parametric equation into a rectangular equation? Oh, you want me to scroll back up? Sure. Yeah. Okay, I'll write that down right after someone asked me to scroll back up. Is that what you wanted to see, Edith? Okay, cool. Okay, thank you. So we have a name for this. When you let's see if I can do the highlighter. When you transform the parametric equation into a rectangular equation. Oh my god, that's so cool. Look at that. We have a name for that. Elimination of the parameter. Okay, so what you could do is take your two parametric equations, eliminate the parameter, get a rectangular equation, and then take the derivative. Okay, so let's do that as an example. Actually, we'll leave that like that. I'm going to give us a little more space. There we go. So we have our parametric equations, x of t equals 2t plus 3, that one right here. We have our second parametric equation, y of t equals 3t minus 4. We've got our domain. Okay, just to remind people, what was the first step on eliminating the parameter? What was step uno? Solving one of the equations for t, yeah. So let's do that for y. So we have y equals 3t minus 4. So we'll get y plus 4 equals 3t, which means we get y plus 4 over 3 equals t. Cool. Now what do we do? Yes, substitute it into the other equation. So we'll take this and substitute it into x equals 2t plus 3, which means we're going to get x equals 2 and t is equal to y plus 4 over 3 plus 3. Okay. So let's multiply everything by 3. 3x equals, and let's distribute the 2, 2y plus 8 plus 9. Let's simplify. 3x equals 2y, 8 plus 9 is 17. Cool, let's solve for y. Let's see, can you see? I can see over there, so we're gonna move up here now. So 3x minus 17 divided by 2 equals y. Cool, so now we have like a y equation. So now it's like pretty straightforward to find the slope of the tangent line. You would just calculate dy dx. You can forget about that half. So if you take the derivative of this, what are you going to get? You get 3 halves. And that makes sense because we had an equation of a line, so it's going to have a constant tangent line everywhere. Okay, now this wasn't that bad because our parametric equations were fairly simple, right? Like we were, without too much difficulty, able to eliminate the parameter, and we were able to, without too much difficulty, take the derivative. However, there are cases in which this would be a lot of work. So what we want to do is we want to figure out how to find the slope of the tangent line without going through all of this hassle. And it actually ends up being pretty simple. You can deal with the parametric equations individually. And what might be your guess as to how you would find what you would use to find the slope of the tangent line for a parametric equation? Any guesses from anyone? Like what might you do to the parametric equations themselves to find the slope of the tangent line? Yeah. So actually let's look at this. Let's work with y prime. So you can take the derivatives of the things individually. So remember, y is 3t minus 4, so what's y prime going to be? Okay, nice, 3. You could also take the derivative of x. So what's x prime going to be? And then, oh my god, what do you think the formula is to do this? What do you think dy dx is always going to be equal to? Because if you look at these two... Well, no. I meant by in terms of the equations the parametric equations themselves. Right, except for we're going to call it y prime t over x prime t. Because we're not going to say dy dt, because when you write it that way, you're sort of implicitly thinking of them as rectangular equations. So we're going to write the y prime way of doing it. Does that make sense? But yeah, I totally get what you're saying. Well, yeah, what should the bottom not be equal to? Yeah, your derivative should not be equal to 0. Otherwise, yeah, that's not going to work for you. Okay. So this ends up being this formula ends up being a lot easier to use as opposed to this process that we outlined above of, eliminating the parameter, finding the rectangular equation, and then taking the derivative. Because you can just work with the pieces individually here. Okay. So let's do some examples with this. A constant? Oh, okay. So let's look. It's actually a good question. So let's make up an example to spitball the case you're talking about here. Make a little more space. So if I'm understanding your question, let's write an example. You're saying, okay, what if x of t is like a constant like 5? And y of t is, let's just say t. Sound good? Okay, cool. So let's look at like what the graph of that would look like. So I'm going to insert an xy axis. Okay, and then we're going to quickly also make a little table for ourselves. So t, x, y. Okay, so no matter what you plug in for t, what is your x always going to be? Cool. So we're just going to do like 4 points. So t equals 1, 2, 3. So your y is just your t value, so you get 1, 2, 3. So if you start graphing this, you get 5, 0. 1, 2, 3, 4, 5. 5, 0 is right here. And then you get 5, 1. That's right there. 5, 2. That's right there. 5, 3. That's right there. So what sort of shape do we have here for our graph? Right, but it's this particular type of line. Maybe go from there to there. What sort of line is this? It's a vertical line. And what do we know about the slopes of vertical lines? They are what? They're not 0. 0 is flat like this. They're undefined because they're vertical. Because what's the slope formula? Slope formula is change in y over change in x. What is the change in y going to be? It's going to be some constant. Let's just say it's always going to be like some number c. And then what are you dividing by? The change in x is always 0, right? So it ends up being undefined. And this makes sense because when you take your derivative, x prime of t, what do you get? 0, and that's going to end up on the bottom of the formula, right? Which will always make it undefined. So it's undefined in the case where you have a vertical line, which is exactly what you should be expecting. Does that clear that up or no? I need some reacts. I know it's not early in the morning, but okay, cool. Okay. Oh my gosh, is that your real name? Herv? Is your name those 4 words? Oh, cool. I like it. Okay. So let's do some other examples. Let's give ourselves some space. So let's do this for, let's do it for a parabola. Oh, damn, let's go to white. Okay, so let's calculate dy dx for the parametric curves. Okay, this will be our first one. So let's make our first set be x of t equals t squared minus 3. Y of t will be 2t minus 1, and will be defined from negative 3 to 4. Okay. So let's just spend a little bit of time like drawing this and like verifying that it works. So I'm going to insert an xy axis. Oops, sorry. Do that again. I messed up. Okay, cool. We've got our... Yeah, sure. You're talking about like the domain, like from negative 3 to 4? I mean, I guess if there doesn't say that anywhere, I would assume that t is just a real number, so that you could plug in anything. Does that sort of make sense? Like, if it doesn't say anywhere, that's probably what's going on. It's a good question, though. Oops. Okay, I wanted to erase that. Just okay, what the hell's going on? There we go. Okay, so let's plug in some numbers. T, X, Y. So when you plug in negative 3, you get 9 minus 3 is 6. When you plug negative 3 into y, you get negative 6 minus 1, which is negative 7. Let's plug in another number. Negative 2, you get 4 minus 3, which is 1. Negative 2 times 2 is negative 4. Negative 4 minus 1 is negative 5. Let's plug in negative 1. So 1 squared is 1. 1 minus 3 is... 1 minus 3 is negative 2. And then if you plug in negative 1 over here, you get negative 2 minus 1, which is negative 3. So if you look at the y values, what's the pattern? So looking at those y values, let me insert a little more space. Yeah, they're changing by differences of 2. So that makes it easier just to fill all of those in. So you get negative 1, 1, 3, 5, 7. Let's plug in 0 for the x. So if you plug in 0 for the x, you get negative 3. If you plug in 1, negative 2. If you plug in 2, you get 1 again. If you plug in 3, you get 6 again. If you plug in 4, you get 16 minus 3 is 13. Cool. So let's plot this. So 1, 2, 3, 4, 5, 6, negative 7. 1, 2, 3, 4, 5, 6, 7. So you get a point like right here, and then you get 1 comma negative 5. That's like right here. So you're going in this direction. Okay, and then you get negative 2, negative 3. That's like over there. Okay, negative 3, negative 1. That's like right here. Okay, and then it keeps on going like this because you could see the parabola forming. Okay. Except for it goes a little further, it goes all the way out to like 13, so it would keep going over to here somewhere. Okay. So, if we want to find the slope of the tangent line at one of these points, we know that the formula is dy dx equals y prime over x prime. Okay, looking at the derivative of y, you get 2. And looking at the derivative of x, you get 2t. Which means that it simplifies to 1 over t. Okay, now notice, this is a little annoying. What don't we like about this equation? There's like one drawback to this. Like, let's say I gave you a point right here. Normally, how would you think of this point? Does everyone see the little red point that I put on the graph? Like, if you look at that point, you don't know what its values are, but how do you think of that point? Right. So you think about points in terms of x and y values, right? Okay. Does this formula help you for figuring that out right there immediately? Like the one right over here, the dy dx. What is this formula actually in terms of? Right. So you would have to figure out, like, oh, if this point right here is 1, 3, like I think that was Edith who said that, you wouldn't think about it as the point 1, 3. You would have to think about it in terms of what? Right, exactly. You'd have to figure out the associated parameterized value. Okay, well, why is my hand up? Somehow I raised my hand in the thing. That's funny. I just noticed that. Wait, is there someone else called Emmanuel Garcia? That's hilarious. Did someone here also have my name? Their hand is up. Does everyone see that on the Zoom? Oh shit, who are you? Person with my name. Yeah, what's your question? The 2's do cancel. It is. It's 1 over t. It says right down here. You don't see that? It cancels right down there. Okay, I'm like wondering who this person is now. Interesting. Okay, anyways, yeah, it's in terms of t. So if you choose a point on there with x and y values, you're going to have to work backwards and figure out the t. That's like the one drawback to this. So I just wanted to point that out to everyone. All right, let's do another example. Okay. So let's scroll down. I wonder who's trolling me with my name. Oh my god, do you know, has anyone been in a one of these meetings where you get Zoom bombed? Okay. Someone came in with the name like Bucklau one time into like the class, and they kept on. Yeah, has everyone heard of Bucklau? It's like a meme, I guess. Do we know what I'm talking about, Bucklau? Yeah, I was graced by the presence of Bucklau once. I've never had someone try to, like, you know, use my name on me, though. Don't know why you're doing that, person. Okay. What? I know, yeah, they're my biggest fan. They're like, they got my name. Oh, did they leave? No, they're still here. I think they changed their name, though. Okay, so let's keep going. Let's do another example. Yeah, you know, imitation is the, what is it called? What's the saying? Imitation. Yeah, there we go. Yes, imitation is the best form of flattery. Thank you. So I'm pleased. Okay, so we got B here. Let's do a second example. So for this example, let's do a more complicated one, just so you can sort of see the interesting shapes that you get. So let's do x of t equals 2t plus 1. Let's do y of t equals t cubed minus 3t plus 4. And let's do it from -2 to 5. Okay, so normally when I would do these problems, I would use Wolfram and calculations. So what I recommend that you do is that you use Wolfram to do the graphs. Does that make sense to everyone? Okay, so what I'm going to do is I'm going to open up a Wolfram really quickly. Okay, let me share my Wolfram screen. Oh look, my person left. I'm sad. I'm sorry, you're gone. It was too soon. We never got to know each other. Okay, so you are always going to use Wolfram, like on, what's it called? On Wolfram Cloud. I have the program downloaded. So if you want to graph a parametric equation, what is the command? Do we remember from last time? Do we remember the command? Almost. It was parametric plot. And yet, you have to remember, the first letter is always uppercase. So pretty close. Does everyone see my Wolfram screen where it says parametric plot or no? Okay, perfect. Okay, cool. So then you put the brackets. Now inside of the brackets, you have to put the two equations. So they are 2t plus 1. You put a comma. And then we're going to put t cubed. To cube something, you put the caret. The caret is a shift 6. And then you do minus 3t and then plus 4. Okay, notice that the pair of equations are inside of curly braces with a comma between them. Then outside of the curly braces, you put a comma. And then now, what do you have to put out? After you give the equations themselves, what do you have to give Wolfram? Yeah, so you give the smallest number and the largest number. So we're going to go from, was it -2 to 5? Is that what I said? Is that what I wrote down? Yeah, -2 to 5. Okay, so you press shift and enter. It's thinking, and then here's the graph. Wow. Okay, so I'm going to sort of like, oh wow, that like looks really horrible, that graph. Okay, let's not go all the way to 5. Let's go from -2 to 2. Because, like, does everyone see how, like, the graph just keeps going up all high afterwards? So let's cut it off. There we go, that looks better. And then now what I'm going to do is I'm just going to copy the image. And I'm going to paste it into here. Are we back to seeing where I'm writing? Oh, damn. Okay, let me change the size of that image. I think it's like gigantic. There we go. That looks better. There we go. So that's like way nicer looking. Okay. So what I recommend you do is, like, you can actually do this. That's why I really like Wolfram. Especially if you're like working everything, like if you're working on a computer like this, so you can just like copy the graphs. You can have it graph it for you. And then you can like do the work that you need to do. So what are we going to do now? Let's go and let's calculate the dy dx. which we know will be y prime t over x prime t. So let's see, our derivative is going to be, derivative of t cubed is 3t squared. Derivative of minus 3t will be minus 3. Derivative of 4 is it's a constant, so you get 0. And the bottom you get 2. Okay. So if you wanted to use this on the graph, you would have to go and figure out like, oh, what's the t value of this point right here? So like, let's just do an example. Let's choose t equals 0. So if you wanted to use t equals 0, you'd have to plug in y of 0 and x of 0. If you plug 0 into x, you get 1. If you plug 0 into the y function, you get 4. Oh man, so I made like a pretty good guess there. Oh, sweet. So t equals 0 is at 1 comma 4, which is right there. So we want to find the slope of this tangent line going through that point. You can tell that it's negative, whatever it is. Okay, so let's plug that in. Into dy dx, we will plug in 0, which gives you negative 3 over 2. Boom, there's the slope of the tangent line. I plugged it into my x of t and my y of t. Right, that's what I'm doing right here. No. Because you to get the point, you have to plug it into the original equations, not the derivatives, right? You don't want to plug it into y prime of t and x prime of t. You want to plug it into the original x of t and the original y of t. No, well, yeah, usually it depends. Like in this case, I just sort of chose one. But let's say I gave you 1 comma 4. You could actually work backwards to figure out what that is. How would you work backwards to figure out what the t value is if I gave you 1 and 4? Like, what would you have to do? It's a good question. Okay, I'll answer it. You would have to say x of t equals 1 and y of t equals 4, and you would just set up those equations and solve for them. So you'd get like 2t plus 1 equals 1, and t cubed minus 3t plus 4 equals 4. So does it make sense you could like solve this for t? You'd get 0. So it's not too bad. Does that make sense to everyone? If I gave you a point on the graph with like x and y values, you could just set the x and y parametric equations equal to the values and then solve for t. Let's see, what time do we go until? 9:05. Okay, let's take a quick break. Let's break until 8:35. Give everyone a moment just to relax their brains. Okay, so please return at 8:35. Yo, yo, I'm back. We back, people? Oh, wait, shit. Yo, yo, I'm back. I was muted, sorry. We back. Respond if you're back. Let's get some reacts. I wonder what happened to my clone. I'm so sad. They're like gone. Did you guys? I saw the comments. Like when that was going down. I like wonder what happened to them. But I also saw that someone apparently was in a meeting with a bunch of interns and the president of a company in Fremont, and they got Zoom bombed with porn and whatnot. That must have been fun. Alright. Okay, let's begin. Get back to here. Right after your presentation. Hard to compete with that. Okay, so first derivatives are used for finding slopes of tangent lines. We also want to know how to find the second derivative. So let's talk about that. You got so lucky. So let's talk about second derivative. Oh, wait, what happened? Okay, there it is. Okay, my computer's glitching. There we go. Second derivative. So let's just talk notation for a second. The second derivative is the derivative of the first derivative, which we could just write like d squared y dx squared. Okay, why is looking at it this way not going to help us? Why does writing the second derivative in the way that I just highlighted in green not useful for us? Like, what's bad about it? Well, there's another issue with it. So, like, the part inside of the parentheses here, or the brackets, what variables did it have? What was the variable that it was in terms of when we actually calculated it for parametric equations? Yeah, it was in terms of t. And what is the variable that we're taking the derivative with respect to? To get our second derivative. Right. But if you look right here, the second derivative, it's telling you to take the derivative of dy dx with respect to what? Yeah. So it's asking us to take the derivative with respect to x. And those two don't match, right? It says here, take the derivative with respect to x, but we know that it's in terms of t, right? So we need a different formula. Does that make sense? You can't just take the dy dx, which is going to be equal to y prime over x prime. It's not like you can just take that and then take the derivative with respect to x of it, right? It's not going to work out because the variables don't match. So anyways, we have a formula to calculate this for us. What you're going to need to do is you're going to take your dy dx and you're going to take the derivative of that. And what's the only thing that you can take the derivative of it with respect to? Like, what should I take it with respect to? What's it in terms of? Yeah, cool. So you take d dt, and that's going to be one part of a fraction. And on the bottom, you're going to have dx dt, also known as x prime t. So if you want to like write this out longer, you're gonna have d dt x prime, d dt y prime t over x prime t all divided by x prime t. So these two are exactly the same, they're just written differently. So it makes sense, I replace the dy dx with the y prime t, x prime t. Okay, so if you need to find the second derivative or the acceleration for something, that's the formula you use. I'm not going to bother doing an example. Cool. Okay. So that's all we need to know for derivatives. So what are we going to move on to now for parametric equations? We've talked derivatives, so what should we talk now? It's only logical. I mean, we sort of basically did that. We're not going to review that. We'll move on to a completely different but relevant topic. Yeah, integrals. We could talk about finding a tangent line, sure, but I'm going to assume that you're pretty good at that at this point. So we're going to move on to just doing integrals. So let's draw a, what's it called here? An axis. So let's say that you have some x of t, and you've got some y of t, and it gives you some graph. I'm just gonna like draw some random thing. So here's the graph of the parametric equations. So what we're interested in finding is, let's say you choose between some x value a and x value b. You want to know the area under this parametric curve between a and b. So we would like to calculate we would like to calculate the area under the area under the graph of the parametric curve defined by x of t and y of t above the x-axis and between x equals a and x equals b. Okay, so the question is, like, how do we do that? So if this was some simple function f of x, what would you do? So like if we were just graphing some regular rectangular equation f of x, how would I find this? What would I do? Yes. What would you do? Oh, no, you don't need a, there's no shell method here. You just, I'm saying if this was some regular f of x, how would you find this area in green? I think you're overthinking it. Okay, wait, I think you're calculating it. I'm asking a really simple question. Like, if this was a regular rectangular equation and you wanted that area, what would you do? Like, this is beginning 101B, what I'm asking you. Not length times width. That's too far back. That's too simple. Okay, wait. How do you define the area under a curve between A and B? Yeah, take the integral from A to B. Thank you. Everyone's like way overthinking this. If this was a regular rectangular equation, you would just integrate from A to B. Boom. Done. That's how I was like, oh man, everyone's like just like thinking of all the crap they learned from the other semesters. Like, this is a really easy question. If you want that area, all you do is you integrate the area under the curve, correct? Okay, now what's more complicated for us is we don't have some simple f of x. We have parametric equations now. And it's actually not that hard to do this. So if you're dealing with parametric curves, you're still going to integrate from A to B. And what you're going to integrate is y of t x prime t dt. That's how you get the area under the curve. Okay, so what's nice about this is that you can use the a and b values. You don't have to use the t values when you integrate. Okay, so we'll what's it called? We'll do some examples. Can everyone see the formula? Sounds like it. Let's see, we go until, I know 5, okay cool, we have like 15 minutes, good. Alright, so let's scroll, can I scroll down now? Okay, cool. Any objections to scrolling? I just want to make sure that everyone's like written whatever they need to write. Okay, cool. Scroll down. Let's go for a scroll. Okay, example. Okay, so what should my parametric equations be? Okay, we're gonna have x of t be 2t, and we're gonna have y of t be cosine t, and t will go from 0 to 2 pi. Okay, so I'm going to quickly use Wolfram to graph this, and then I'm going to paste in the graph so we can like take a look at it. So our x value is 2t, our y value is cosine t, and we're going from 0 to 2 pi. Actually, let's go from 0 to, I'm going to change this up a little. Let's go from 0 to pi over 2. Oops, sorry, I'm having that difficulty. There we go. It's like wondering, like, why is this not moving? Okay, let's move it over here. Let's make it smaller. Okay, so hopefully everyone can see that fairly well. Okay, so you can see that, let's plug in some of the numbers. So when you plug in 0, you're going to get the point 0, 1. So this point right here is 0, 1. Let's plug in pi over 2. 2 times pi over 2 is pi. If you plug in pi over 2 into cosine, you get 0. So this point right here is pi comma 0. Any questions on how I got those numbers? Is that making sense? Can we see what I wrote nicely well? Can everyone hear me? Like, no one's responded for a while. I'm just like worried I got like cut off or something. Okay, cool. It's cool. Sorry, I like freaked out when I just like, there's like nothing. I'm like, holy crap, what if I just been like talking into the void and like Zoom disconnected like 10 minutes ago? Okay, cool. So, no questions on that so far. Good. So, what are our limits of integration going to be? What are we going to integrate between? So from 0 to pi. No, not from 0 to pi over 2. You don't look at the t values. You look at the x values. What are my x values? It was 0 to pi. Okay? Those are x values. So that's why I plugged 0 and pi over 2 as t values into my parametric equations to get the x and y values. That's how I got 0 and how I got pi. That's how they end up here in the limits of integration. Okay, now the formula says to find the area under this, all this area over here, I'm going to integrate y of t x prime t dt. So I need to figure out what those are. So my y of t is just cosine t. My x prime t is 2. So I'm going to integrate 0 to pi cosine t 2 dt. So I'm going to pause. Makes sense. Any questions on where any of the pieces came from? I'm going to stretch. So when you do this, you have to think about where the pieces are coming from. You can't just take the t values from 0 to pi over 2. You have to find the x values, the limits of integration, right? I'm integrating from here to here, below this curve. Okay. Now this is not too difficult to integrate. Let's make a little more space. You could factor out the 2, or not factor it out, you can use the integration properties. So this is not too hard. What's the antiderivative of cosine? Yes. So what I'm going to get is 2 sine of pi minus sine of 0. What's the sine of pi? Uh, 0 pi over 2. Yeah, I believe that the sine of pi is not. Oh, whoa, what happened here? What's the sine of pi? Yeah. And what's the sine of 0? Holy crap. This is obviously, I think I just picked a really bad example. This is not the area I was expecting to get. Okay, let's see. Did we like make a mistake somewhere here? What the hell? Oh shoot, I'm so sorry. I was reading the notes wrong. I apologize. No wonder. Okay. Yeah. Okay, my bad. I feel so bad. Okay. Remember how someone earlier said you should integrate from 0 to pi over 2? Yeah, you are supposed to do that. No wonder. I am so sorry. I don't know what I was thinking. Okay, we're gonna have to go back and change this. We didn't have to calculate these values. We can leave them there, but I'm so sorry. Yeah, good practice though. So you do integrate from your A and your B are the limits of the t value. Oh my gosh, I'm so sorry. You don't use the x values. Let's make a little note about this. Sorry. Okay. These are the t values, not x values. No wonder. My bad. Because that's going to change everything now. Because when you plug in pi over 2, what are you going to get? What's the sign of pi over 2? 1, there we go. So you get 1 minus 0, so you get 2. The area under that curve is 2. Yeah, actually, I just thought about that, and it's because what are you integrating with respect to? Yeah. I don't know why I so stupidly said that earlier. But does that make sense, though? Because you're integrating with respect to t, you use the t values. Yeah, so you use the value, the limits for the limits of integration. I'm so sorry. I don't know what I was thinking when I wrote that down, but I ran with it and it was not good. Yeah. Yeah. Mm-hmm. No, that's the cool thing. It doesn't matter. It doesn't matter if your graph looks vertical or something like that. You're still always going to use y of t, x prime of t. Because what will happen is that the parametrically change it. Sorry, the parametric equations will be changed so that it appears more vertical, and you don't have to change anything else. It's already done for you. It's you're thinking about from Calc 2, where it's like if you integrate between. So let me sort of just see if I'm thinking about what you're thinking about. If here's the x and y axis, and here is your curve, you were able to if you wanted to find this area, you would have to switch stuff up, and you would integrate from some y value a to some y value b, right? Is that what? Yeah. So we will get to how to do that. You would have to change some stuff, but we're not going to really cover that in this course. You would only really do that for rectangular equations. Other questions that we want to ask? Okay. So it's pretty straightforward to use this. You plug everything into the formula. Don't mess up like I did. Use the t values, not the x values. We have a couple minutes left, so let's talk about another topic, other things that you can use integration for. So it's very common to calculate something called arc length. So arc length is where, let's draw an x and a y axis. Let's say that you have some parametric equations, x of t, y of t. And let's say the graph looks like this. You start right here and you move along like this. So let's put the little arrows. Okay, let's say that you want to find the distance traveled between the starting point and ending point. That's what we mean by arc length. So what you want is the distance traveled by a point. Actually, let me just type that down. I don't know why I'm writing it out. We want the distance traveled by a point following the graph. Okay, so when we say arc length, that's what we mean. Okay, so you have your x of t, your y of t, and let's say that your y value is going to go from a to b. I'm sorry, your t value will go from a to b. So a and b refer to t values, not x or y values. So we use the letter s to refer to arc length. So whenever you see an s, you know that it's the length of a point moving along a graph. You'll use integration to figure this out. You will integrate from a to b. And the formula is a little crazy. You're going to integrate the square root of dx dt squared. So you're going to take the derivative of your x of t and square it. You could also write it as x prime t squared. And actually, I prefer to write it that way. And then you will add y prime t squared, and you will integrate with respect to dt. And there are two versions of this formula. This is actually equivalent to integrating from a to b the square root of 1 plus dy dx squared dx. Okay, and we'll talk about this more next class because we only have like a minute or two left, so we're just going to end it here. I'm going to click the stop recording. And we'll stop right here because there's not really enough time to like keep going and do more.